In this lecture, we're going to look at using probabilistic models for clustering, probabilistic distributions for clustering data. So we're going to look at probabilistic clustering, and using this, we're going to take a more detailed look at expectation maximization, that approach that we saw briefly in the context of k-means, which uses the same idea, although it is not quite expectation maximization. But we're going to see that here more rigorously in probabilistic clustering, and this will help us then understand in the next lecture hidden Markov models, which are a very important part of sequence analysis in bioinformatics. We're also going to look at how to evaluate clusters, different methods based on the internal properties of the clusters, and also comparing the clusters with external indicators. There will be many equations here, but don't be scared, because what matters is not to try to memorize the equations, but to capture the ideas behind these algorithms. So let's start with the probabilistic clustering. Suppose that we have a probability model for the distribution of examples. So the X is the set of attributes that we know, those vectors that describe our examples. And we have a model that gives us the joint probability distribution of having some particular set of values, each example, and belonging to some group that we're calling Y here. So we can write this in these two ways. So this would be the joint probability distribution of the values of the example and the group it belongs to. And this would be writing the same thing, the joint probability distribution, but decomposing it on the conditional distribution of having some set of values if it belongs to group Y, multiplied by the probability, the marginal probability of belonging to group Y. So some groups may be larger than others. This would not only provide us a way of clustering the set of examples that we have over all of these groups, because we could assign each example to the group for which the joint probability distribution is higher, and we would cluster our examples in this way. We would also be able to generate new examples from those distributions, because we would know what would be the probability distribution of the values of some hypothetical example that came from some group Y. And this is useful in many cases where we have noisy data or missing data. For example, in some techniques like nanopore sequencing, where we actually have real-time data on the passing of some molecules in the membranes, and then we're using that to sequence those pieces of DNA, for example, or when we have microarray data where we have lots of data but quite noisy there, single cell methylation profiles and so on. There are lots of techniques where due to their nature we not only have a large amount of data but also very noisy data, and in those cases having these probabilistic models can be very helpful. Now the problem is that in clustering we do not know what is the group some point belongs to. So we don't have this in our data. Our data is only the X, the values that we are measuring, and the groups is something the model must give us somewhere during training, as we do clustering. So recall from what we saw with the k-means clustering, this idea that we have a set of observed data, X, which are the values associated with each example, but the groups the examples belong to, we are not going to call them Y, we're going to call them Z. This is a mere convention which is for latent variables. This Z is the set of groups our data belongs to, but we don't know what they are at the beginning. And also we have some parameters for our model that we want to adjust, and we want to adjust them so that we have the parameters that maximize the joint probability of having those particular data belonging to those groups. So this is the idea here, the maximum likelihood. We have this likelihood function, which is a function of the parameters, the data that we have, and the groups the points belong to, that gives us this probability, the probability, the joint probability of the groups and the data, given the parameters that we have. So if we maximize this, we obtain the best parameters, and these will then lead us to the correct groups. But note that everything now depends on each other here. So we have this problem that we can solve with the expectation maximization method, like we saw in k-means. But let's look at this more rigorously in the context of probabilistic clustering. We're going to look at Gaussian mixture models, which is a method of probabilistic clustering where we are considering Gaussian distributions. So if we have Gaussian distributions in one dimension, they have this shape. There is this scaling factor here so that the integral adds up to 1. But then the shape of the curve is determined by the mean point, the average here. For example, in this blue curve will be 0, in this green one would be -2, and the variance, or the square of the standard deviation here, which gives us the spread of the curve. So we could define one of these probability distributions with these two parameters, the mean and the standard deviation, which would fix the shape of the curve and the position. And we could say that some points are drawn from this distribution, which is a normal, a Gaussian distribution, using this mean and standard deviation. If we go into higher dimensions, not in one dimension, but in n dimensions, this becomes a bit more complex. We have to consider this covariance matrix sigma here, which basically is a matrix that gives us the shape of this Gaussian distribution in all the different dimensions. But the idea is the same. We are multiplying these vectors between each point and the central point of the Gaussian distribution. We are multiplying this by the covariance matrix sigma here. The scaling factor also depends on these modulus of the covariance matrix. But in any case, we can define these Gaussian distributions with the central point and the matrix that tells us how it's spread out in the different directions. But what we can do with this is, if we have a set of Gaussian distributions, we can add them and have some more complex distribution, which is the sum, the mixture of different Gaussians. And we can add different Gaussian distributions with different weights. So we can have a small bit of the yellow one and a large part of the blue one, and so on, and add things together so that the sum of everything still has an integral of 1. So it's a probability distribution, but the shape is arbitrarily complex the more Gaussian curves we mix together. So this is just a one-dimensional representation, but we can do this in n dimensions just using the Gaussian distributions in n dimensions. So the mixture model of k Gaussian distributions will be this probability distribution that we can obtain by summing all of the individual Gaussian distributions here. Each one has its own central point and its own covariance matrix, and each one has a particular weight. This is a weighted sum of all of these distributions, and the constraint here is that the sum of all these weights is 1, so that everything, this sum, works as a probability distribution. The integral over all the space adds up to 1. So all of these values must be between 0 and 1, and they must add up to 1 so that we have a probability distribution. But this is the basic idea of Gaussian mixture models, which is to mix together a set of k Gaussian distributions, each one with its own particular weight, such that all the weights are between 0 and 1, and they add up to 1 so that we have a probability distribution here. Okay, so this is what we are creating as a probability model of how our data is distributed in the different clusters. So each of these Gaussians would represent a cluster, and the total distribution is the weighted sum of all of those Gaussians. Okay, so now let's see how we can compute these parameters that we need. Basically, we are going to need the contribution, the value with which each Gaussian distribution contributes to the sum, so this pi k for each Gaussian. Also, the central point of each distribution, this mu k, and the sigmas, which are the covariance matrices for all of these distributions. So we need to compute all of these parameters, and we need to compute them so that they are as adjusted as possible to the data that we have. And now the way we are going to do this is by maximizing the likelihood. That is, we want to find the parameters that maximize the probability of having those points distributed in that particular way and coming from those particular Gaussian distributions. So to do this, we're going to create an additional variable, this z variable, which is the one that tells us to which Gaussian distribution each point belongs to, and such that the membership value here or for z is either 0 or 1. So each point either belongs to one cluster or not. It came from that Gaussian or not. And this adds up to 1. So basically, each point can only belong to one cluster. It has 1 in that corresponding cluster, in that corresponding zk variable, and has 0 for all the others. So now we can look again at this distribution, which is the joint probability distribution of all the points that we have being placed in those particular positions that they are, and the corresponding membership values for these z variables that indicate to which cluster each point belongs. And the joint probability distribution here is what we want to maximize by adjusting our parameters. We can write this also as the probability, the marginal probability of belonging to any particular cluster, to each particular cluster, and multiplied by the probability of being in that position, having that set of values, the example, if it belongs to that cluster. So this marginal probability here, so the probability of the value of z for cluster k being 1 is the contribution of that cluster k to the overall Gaussian mixture. Basically, this is abstracting from all the positions of the points. We are not looking at the position of the points, but a priori, before even knowing where the points are, we can consider the probability of a point belonging to a particular cluster is the amount or the fraction that this cluster is represented in the Gaussian mixture. The larger this value, the larger the contribution of that cluster, the greater the number of points that will belong to that cluster. And also we can compute the probability of a point having some particular set of values if it belongs to some cluster, by looking at the probability distribution for that cluster. So the probability distribution for that cluster is a Gaussian probability distribution with its particular mean point and covariance matrix. So if we know that point x belongs to this Gaussian k, we know the probability of point x being in these coordinates, because we know what are the parameters for the Gaussian distribution k. Okay, so we can now write these probabilities, the probability of the point being in some position and coming from a particular distribution. We can write this using the parameters for the different Gaussian distributions, and if we sum everything together and consider how much each Gaussian distribution is contributing, what we have here would be the distribution of all the points. So these are the points coming from all the different Gaussian distributions. So now, how can we compute this? The problem that you can see here is that the probabilities themselves, the ones that we are trying to maximize, will depend here on the parameters, and will depend also on these z variables that we cannot observe. So this is the same problem that we had in k-means. We could not simply maximize likelihood because we don't know to which cluster each point belongs. So this is what how we can solve this is with expectation maximization, and we're going to first compute the probability of a point belonging to a cluster if we know what is the position of the point. So note that we can do this in reverse. We can, if we know the point belongs to a cluster, we can know the probability of it being in some position because we have the parameters, if we have the parameters for that particular Gaussian distribution. But to do this in reverse, we can apply Bayes' rule, and basically what we need is the prior probability of a point belonging to cluster K. This is just the fraction of points that belong to cluster K, that contribution of K to the mixture, and then the probability of this point being in that particular position if it belongs to cluster K. But then we divide this by the sum of the same terms for all the different clusters. So basically we can see this as the probability of a point belonging to cluster K is the fraction of this probability, the marginal probability of belonging to cluster K, and the probability of the point being where it is if it belongs to cluster K, divided by the sum over all the possible clusters. So it's this ratio which we can compute if we know the parameters, because the marginal probability of belonging to cluster K is just this pi K value here, which is the fraction with which the Gaussian distribution K is contributing to the complete mixture. The probability of the point being in that position, if it belongs to cluster K, is given by the distribution of this Gaussian curve with the parameters for cluster K. And then we can do the same thing. We can add the same expression for all the clusters and see what fraction we have here. So if this fraction, if this is 10% of the total, for example, then the probability of this particular point belonging to this cluster K will be 10%, because that is the fraction that we get here. So to avoid carrying around all of this expression, let's call this the gamma of that particular point n belonging to cluster K. And now we can use this expression instead of this, but basically this is the probability of point n belonging to the cluster K, given that we know the coordinates, the values associated to point n. Now we want to maximize the logarithm of the likelihood of our parameters. So basically we want to maximize these probabilities of the data given the parameters that we need to compute. These are all the pi values, all the mu's for the centers of the distribution, and all the sigmas for the covariance. So if we want to find the maximum of this expression, we want to find the point where the derivative is 0, and now all we need to do is to compute the derivatives with respect to the different parameters that we are computing. So without going into much detail here, setting the derivatives to 0 with respect to the different parameters for the centers of the different distributions, what we have is a sum over all the points of the probability of that particular point belonging to distribution K multiplied by the coordinates of the point. So basically we are considering the center of the distribution to be given by the weighted sum or the weighted average of all of these points, and the weight with which each point is contributing is the probability of the point belonging to that particular distribution. So this would be what tells us the best position for the central point of the distribution. Okay, so now note one difficulty here is this, although this is intuitively, basically we are computing an average of all the coordinates, but we are giving different weights for different points based on the probability of belonging to that cluster. This is similar to what we did with k-means, but with k-means we did not have this probability. Either it belonged to the cluster or not. So that was what we were doing there. And sorry, here, I skipped backwards. Okay. So with k-means, we would simply consider that the point belongs to the cluster. Here, we are considering the probability of the point belonging to the cluster. Now, one difficulty here is that the probability of the point belonging to the cluster is something that we can compute based on the parameters, but which we need to use to compute the parameters of our model. So you can see here the need for the expectation maximization algorithm, because we don't know a priori the probability of belonging to a cluster if we don't have the parameters, but after we compute that probability, we can now compute a better estimate of those parameters. This scaling factor here for the average is not quite the number of points, because the points are not contributing with a value of 1 each, but it's simply the sum of all these probabilities. So this gives us an average that is weighted differently for different points. So this is for computing the central position of each Gaussian curve. To compute this, the covariance matrices, we do the same thing. So it's this weighted average for all the points considering the center of the distribution. Basically, this is the expression for setting the derivative with respect to the covariance matrix to 0. And finally, the fraction with which each particular Gaussian distribution K contributes to the mixture. And this is given by the fraction between the effective number of points, so the sum of all of these probabilities for the cluster K, for the Gaussian distribution K, divided by the actual number of points. So if one Gaussian distribution receives, say, 30% of the probabilities, the total probabilities for the points, all of these sums, then it will have a 0.3 here in its parameter pi. Okay, so this is now how we can solve this problem with expectation maximization. First, we start with an initial guess of our parameters, and this initial guess allows us to compute the probability of each point n belonging to each cluster K. And from this probability, we can now create the likelihood function that we have here, and which we are now computing the derivatives for computing the best values for the parameters. So note that we start with an initial guess for the parameters, and now we use that to write the likelihood function, and we maximize the likelihood to recompute the parameters. And this is what we're going to do now until convergence. We use the latest guess of the parameters to recompute the probabilities. We use these probabilities to create the likelihood function. So this would be our estimation step. And now we maximize this likelihood function and recompute the parameters again. And we keep doing this until we have convergence, until the parameters are no longer changing or no longer changing significantly. To illustrate this, suppose that we have this data set, all of these points here, and we are computing a Gaussian mixture model with two Gaussian components. This is after the first pass. We started with some random set of parameters. We used those to compute the probabilities of points belonging to each Gaussian, and now we computed the parameters again. So these circles represent the center and the standard deviation of each Gaussian distribution. If we move on now to the second pass, we improve the parameters here, and eventually we reach convergence here. We stop changing too much. So this would be the shape and position of the two Gaussian curves, represented here by the center point and the standard deviation, that would best capture the distribution of these points. Note that this doesn't fit the data very well, because clearly we have 3 clusters, but we are only using 2 components on our Gaussian mixture. We can improve this by using 3 components. So in this case, I'm representing them red, green, and blue. And again, this would be the first pass, and then 2 passes, 3 passes, and so on, until everything converges. So you see that using this expectation maximization approach, we use an initial guess of the parameters to compute the probability of the points belonging to each particular curve, to each particular Gaussian distribution, and then we use that to maximize the likelihood by adjusting the parameters again, and so improving the shape and position of the curves. And we keep iterating this, going back and forth, until we reach convergence. And in this case, we have 3 Gaussian distributions fitting nicely with the 3 different different clusters of points that we have here. If you want to use this in scikit-learn, it's very easy, because we have this Gaussian mixture class in scikit-learn. You can set the number of components. By default it's 1, but you can set the number of clusters that you want. There are different options for the covariance type, because you can set constraints on the covariance to limit the number of free parameters that you have. For example, a spherical covariance has the same variance in all the directions. It will be completely symmetrical in all the directions. The diagonal set sum of the different values must be equal, and so on. So you have different degrees of freedom for the covariance matrix here, the maximum number of iterations, but basically the most important parameter would be here the number of components, which is the number of Gaussians in the mixture, and this will give you the number of clusters at the end. Okay, so we saw different types, different forms of clustering. In fact, in the beginning, we saw hierarchical clustering when we looked at UPGMA and phylogenetic trees, so I skipped that part here in clustering. But in this later part of the semester, we saw clustering based on prototypes using k-means. We saw clustering based on density using dbScan. Now we saw probabilistic clustering with Gaussian mixture models, and there are many different ways of doing clustering and different algorithms, different parameters that you can set. So one problem that arises is how we can validate the result of clustering. After we have our results, how do we know if they are good or bad? So basically, I'm going to give a very brief overview of this problem, looking at both internal indexes and external or relative indexes. The difference here is that with internal indexes, we are only looking at attributes of the clusters themselves. And using these external or relative indexes, we are comparing our clusters either with some external labels, as we can do in supervised learning where we have labeled data, or with other clusters. For example, we can compare different clustering algorithms to see how much they agree or disagree. Now, one particular problem with clustering, and that makes it very different from what we saw previously with classification, is that we do not have an objective, a clear-cut way to measure success with clustering. If you're doing classification, you can always measure how much you're getting right or wrong in your predictions. But the idea of clustering is to try to help us understand and extract information from the data. And so it depends a lot on what we want to do with the data. And there is no clear way of saying if a cluster is good or bad, except by thinking about what we want to obtain from the data. So this is a problem where validating the results of clustering is very difficult and even frustrating, because it depends a lot on what you want to do with clustering. But let's look first at what we can do if we are in a setting of unsupervised learning where we don't have external labels and we are not comparing to other clusterings. We are just trying to assess how good the clusters are without referring to any external data. So we are using only these internal indexes. And we can look at things like how cohesive the clusters are, how close together the points are within a cluster, how well separated they are, things like summing the squares of the distances to the center, and so on. And we're also going to look at this silhouette score, which can be useful in some cases to evaluate clustering. But this is just to give you a general idea of the kind of attributes that we can look at when evaluating clustering. So cohesion comes from this notion that when we are clustering, we want the members of each cluster to be similar to each other. So basically, cohesion we can measure by summing for all the pairs of members in a cluster. So this would be for cluster X belonging to cluster I and Y belonging to cluster I. We are measuring the similarity of these elements. So this is deliberately vague. I'm not specifying exactly what this S is. If this is a similarity, then greater cohesion will come from a greater sum of the similarities, because the points that are more similar will have a larger similarity. Conversely, if we are measuring dissimilarity or distance between the points, then we have more cohesion if this sum is smaller. That is, the points are not distant from each other. But the idea is basically that we are measuring this similarity between the points or distance and looking at the pairs of points in the same cluster. And so we have an idea of how tightly together the points that belong to the same cluster are. We can also look at the separation between clusters. So we can use the same general idea of looking at pairs of points, but in this case we are picking one point in cluster I and another point in cluster J. And now we are comparing the clusters I and J by looking at how similar the points from I and J are. If they are very similar, then the clusters are not very separated. If they are very distant or very dissimilar, then the clusters will be well separated. If we are looking at prototype-based clusters like k-means, then we can actually skip all of these pairs and just look at the prototypes. So cohesion we can measure by comparing each point in the cluster to the prototype that represents the cluster. For example, the centroid in the case of k-means. If all the points are very close to the centroid, then the cluster is very tight and cohesive. If the points are very spread out, then there is less cohesion in the cluster. And the same thing, the separation between clusters, we can just look at how separate or close together these prototypes are, these representatives of the clusters. But this, of course, if you're doing, for example, density-based clustering with dbScan, then you don't have this same possibility, but you can always use this approach of looking at the pairs of points. This is what we can do in silhouette score. Basically, silhouette score tries to bring together both of these concepts, how close they are, the points are within each cluster, and how distant they are between the clusters. Of course, if we are actually using distances, we can also look for each cluster at the distances between the points and the centroid. So this would be, for example, the square of the distance. It would give us a sum of squares for all of the points, where we are adding all the distances between the points and the corresponding centroids. So if we do this, if we have a smaller value, then it means that for all our data, the points are close to the centroids. If we have a large value, then everything is more spread out. But with silhouette score, we actually use distances to bring together these two ideas, the cohesion and the separation of the clusters. And we're going to compute for each point I, what is the average distance to all the points in the same cluster. And this will be the A factor for point I. And B, the B factor here is the average distance to the points in the nearest cluster. So this is a different cluster, but the one that has the lowest average distance. And now the silhouette score will be the difference between the distance, the average distance to the nearest cluster, minus the average distance to the points in the same cluster, this value here, and divided by the maximum of the two. So this will range from any value between -1 and 1. And basically, if the distance to the nearest cluster is very large and the distances within the cluster are very small, then this will go close to 1. 1 would be the maximum. A silhouette score of 1 indicates that the points are all very tightly close together in the cluster and very far away from the other nearest cluster. It can be -1 if we have the inverse, if the points are very close to points in a different cluster, but are very far away on average from points in the same cluster. So this would be a very strange clustering and would be completely counterintuitive. You can, with scikit-learn, easily compute silhouette score, which is using this function. This averages the silhouette score of each individual point over all your data set. So what you need to do is basically give the coordinates of the points and the labels for the clusters they belong to, and this function computes the silhouette score for your data with those particular clusters. Okay, so some examples. Suppose that we are doing k-means clustering on this data here. We use k equals 3 for k-means. So we have these 3 centroids. These are the membership assignments of the points to the different clusters. So you can see that these are very well separated and very tight together. And this is a silhouette score close to 1, 0.73. If we don't have, for example, the right number of clusters, we don't got k right, in this case k equals 2 instead of 3, we note that the silhouette score is now lower because there is this cluster where points are farther apart, and then there is this frontier between the green and red clusters in which points are very close together. So those A's and B's now change and we have a smaller silhouette score. So this for this particular kind of clusters where you have globular clusters, the silhouette score can help you fine-tune these parameters such as the k value so that you get the best match between the k and the actual number of clusters that you would intuitively have in the data. Of course, this does not work very well if the clusters are not globular. Not only k-means has problems with those clusters, but then the silhouette score may also not be very good. So in this case, the problem is with k-means. You see that there is a centroid there that assigns these points to the blue cluster, and then these points here get assigned to the red cluster and these to the green. So now the silhouette score is not very good, and these are the clusters as computed by k-means do not seem to match very well the structure of the data. But this is also because k-means is not very good for this kind of data where things are anisotropic. The clusters in this case are all spread out in this diagonal, and since k-means assigns points to the cluster with the closest centroid, it cannot make this kind of distinction here. Also, you can have problems if clusters are spread out differently in the case of k-means. So you see that we have a small tight cluster here, then we have a more spread out cluster here and a tight cluster here. But with k-means, you always have the frontier in exactly the center between the two centroids, and so this lowers the silhouette score in this case because it becomes a bit confusing the way the clusters are separated. So this particular kind of disposition of points, it would be best to use Gaussian mixture models instead of k-means for clustering these ones, because here you could have a Gaussian with a tighter distribution with a lower variance, and here one with a larger variance, and so on, and take into account these different sizes, these different spreads of the points in the clusters. Silhouette score can be very poor for evaluating clusters that are not compact and round like the ones that we saw earlier. For example, using dbScan, we obtain these two clusters here, and this is really something that intuitively seems correct, because these points seem to go together and these points form a different group. But this gives us a very low silhouette score because we have low distances here between the clusters and have large distances within the clusters. So now we get the A's and B's, those factors, very close to each other, and the silhouette score is low. But note that in this particular case, the silhouette score is not telling us anything very useful about the clustering, because it's telling us things are bad when actually they are not really that bad. The clustering is very good. So pay attention that the silhouette score is giving us a measure of cohesion and separation of the clusters that works well for compact globular clusters, but not for clusters with different shapes like this. Okay, so another way we can use to evaluate clusters is to look at external indexes. In supervised learning, we saw this idea of the confusion matrix, where we can have this true positive if we get our prediction correct. So suppose that we have some classifier that is predicting class 1, and the example actually belongs to class 1. So this would be a true positive because our classifier is telling us it's a positive example, and it really is a positive example. A false positive would be when our prediction is telling us the example should belong to class 1, but actually the example belongs to class 0. So this is giving us a false positive. This can happen, for example, in medical tests or things like that. You can have a false positive when the test is telling us something that is not correct. So it's telling us it's positive when it's not. The true negative occurs when we predict the example to be negative, and it actually is a negative example. But then we can also have a false negative if the example is in the positive class, in class 1, and we predict it to be in class 0. So this is something that we can do with supervised learning, with classification, those techniques that we saw previously, like logistic regression, for example. But it's not really something that we can do in clustering, because it does not make sense to try to match the exact label that we have on a cluster, for example, cluster 1, with the label of a class 1, because the labels on the clusters are arbitrary. If we want to cluster like this, for example, this could be cluster 0 and the green one could be cluster 1, or it could be the inverse, the blue one cluster 1 and the green one cluster 0. It doesn't matter. In clustering, the labels are arbitrary. So we cannot build a matrix like this with clustering. What we can do is, instead of considering each particular example, we can consider pairs of examples. And now a true positive would be a pair of examples that belongs to the same external group, for example, a pair of positive examples that we placed in the same cluster, because if they belong to the same external group, they should be in the same cluster. And suppose that we had these two groups, green and blue, previously defined. So if we take a pair of points in the blue and they belong to the same cluster, this is an example of a true positive. They belong in the same group and we place them in the same cluster. A true negative would be a pair of points that come from different groups and we place them in different clusters. So this is the equivalent of what we would have here in classification, but with clustering we are looking at the pair. The pair cannot be in the same cluster because they are not from the same group, and so this would be a true negative. And this would be two examples where clustering, when compared to these external labels, gets the result right, because it either places in the same cluster points that are labeled the same, or it places in different clusters points that are labeled differently. These are examples where clustering would get things wrong, which would be placing in the same cluster points that come from different labels. This would be a false positive because our clustering algorithm is telling us they should be together, when actually they should not be together because they come from different groups. Or conversely, if we are placing in different clusters points that actually come from the same group. This would be a false negative because our clustering algorithm is telling us they do not belong together, when they actually really belong together because they come from the same group. Okay, so if we do these kinds of computations looking at all the pairs of points, we can build something similar to this matrix here that we had in classification. And now we can compute, for example, the precision, the recall, the accuracy, and so on. So basically, the equivalent of the accuracy in this context would be the RAND index, which is the number of true positives and true negatives, that is the sum of the pairs of points that come from the same group and were placed in the same cluster, and that came from different groups and were placed in different clusters. So everything our clustering algorithm got right, divided by the total number of pairs of points. And this is called the RAND index, and it's an equivalent, an analogous to accuracy. It means it gives us the fraction of correct decisions that our clustering algorithm did. But we have also the analogous of precision, recall, F1, and all the different measures that we can use in classification. We can compute the analogous here by looking at the pairs of examples and seeing if examples from the same group are in the same cluster, or if examples from different groups are in different clusters. So this would be the diagonal here where our clustering gets things right, or if our clustering is mixing things together. So it's putting in the same cluster things that come from different groups, which would be the false positive here, or in different cluster pairs of points that come from the same group. So this gives us analogous to all of those measures that we had in classification. One problem with the RAND index is looking at points in different groups, for example, the true negatives here, is that by chance this can get artificially high. Because if we have many different clusters, then simply at random, many pairs will be assigned to different clusters, those that come from different groups. So if we have many groups and many clusters, it will be very easy by chance to get lots of true negatives. We are simply placing them in different clusters. So we can compute an adjusted RAND index that solves this problem by subtracting what we would expect the RAND index to be if we were to cluster our examples at random. So this is a correction for this effect, for this tendency to overestimate the accuracy of the clustering. And in this case, because we are subtracting this value expected at random, the adjusted RAND index can actually be negative and not just between 0 and 1 like the RAND index. This is more complex to compute because we need to compute these expected values, but you can do that easily in scikit-learn by using this adjusted RAND score function that gives you the adjusted RAND index here. Okay, so to sum up what we saw probabilistic clustering. This is another approach to clustering and comes up to basically three approaches that we used as examples of clustering: k-means, dbScan, and Gaussian mixture models. These are only examples. There are many other methods of clustering. We even saw hierarchical clustering methods like UPGMA in the beginning of the semester. And if you want, you can explore in scikit-learn. There are lots of demos of different clustering algorithms. But the main reason for looking at probabilistic clustering now was to get a more detailed look at expectation maximization. So the idea is that we have this first expectation step where we use an initial guess of parameters to compute all the probabilities of membership that allow us to write the likelihood function. And then we do the maximization step where we maximize that likelihood function in order to obtain a better estimate of the parameters. And if we do that iteratively, we keep improving the parameters that we have until we reach convergence. We also saw the problem of validating clusters, both in an unsupervised context where we are using internal indexes, looking at the characteristics of the clusters themselves, and also with external indexes that can be, in the context of supervised learning, can be actual class labels, so groups that we have in the data, or in the context of comparing different clusterings, can be simply the labels obtained from other clustering.